All right, so today we are going to find inverse functions, and we are going to do this both graphically and algebraically. And so we're going to start with graphing the inverse. Graphing an inverse amounts to just switching the x and y values of each ordered pair. And so your inputs are going to become your outputs, and your outputs become your inputs. That's essentially what an inverse function is. An inverse undoes the original. And so I like to think of the inverse function as the undo function. And so if we take an x value of 3, put it inside a function, and it turns into a 9, the inverse function would take that 9 right back to the original 3. And so that would be the inverse function. And we use a little -1 in the exponent kind of the letter f. So if we have f of x, f with a little -1 up in the air would say inverse. So f inverse would take 9 to 3. And so 9, 3 would be a point on the inverse graph, whereas 3, 9 would be a point on the original graph. And so if we have an entire table of points, and so if this were the original function, to graph the inverse function, we take all of these x values and put them in the y, and the corresponding y values would then go in the x. And so this point, 0, -1 on the original, is now -1, 0 on the inverse. 3, 2 becomes 2, 3. Notice if we have a negative value, for example, this -5, we didn't change the sign to positive. We just flipped the inputs and outputs. Don't change any signs in this. And so to do this by hand, if we are given this original graph with the points 0, 2, 1, 5, 5, 6, and 8, 9, to graph the inverse function, we would put the y's here, so 2, 5, 6, 9, and the x's here, 0, 1, 5, 8. And so if I graph this, I now have 2, 0 from this point. I have the point 5, 1 from this point. I have the point 6, 5 from this point, and 9, 8 from this point. And so I recommend you connect the points as you go instead of waiting till the end like I just did, because sometimes the points will be all over the place. And so you really want to know which points have a line between them. And so this is the inverse graph, whereas the blue is the original. And something you may be noticing about this graph is if you were to draw the line y equals x, the slanted line, y equals x, these are reflections mirrored about that line. So that's how you can recognize inverse graphs, is if you draw this slanted line, there should be a mirror image of the inverse to the original. Okay, and so when the relation is a function, sometimes it will be a non-function, but if it is a function like f of x, we write the inverse function using that -1 notation that says F inverse. That's not raising something to a -1. Sometimes they use this -1 as reciprocal. Mathematicians reuse notations over and over and over again, which gets really confusing. So you have to know the context. And so when you put a -1 on a function, it means inverse. And so just like we talked about on the previous slide, your input 3, if it becomes a 9, your inverse function would then take 9 right back to 3. And so this particular function is adding 6 to whatever your input is. And so if I picked another input value, let's say 1, if I add 6, the output would be 7. And so the inverse function, we talked about that being the undo function, it would take 7 right back to 1. And so if the original function is adding 6, our inverse function would have to take away the 6 in order to take our outputs back to the original inputs. And so algebraically, if we're given a function like x plus 6, we can find what the inverse function is. So if we had x plus 6, the inverse function is x minus 6. In this case, it's really obvious what the inverse function would be, but that is not going to be the case later in this course. And so we have a process for finding it. You first replace this f of x notation with the y, and then you switch your x and y positions. So x would come here, and y would come here. And then you re-isolate this y. And so to solve for this y, I would have to subtract 6 from both sides, leaving me with x minus 6 equals y. And so once you've isolated y, you're ready to replace that y with your notation, f inverse of x, which is how we get this equation here. And so we are going to do a few examples of that. And so example 1, this is our first function, f of x equals x minus 1/2. And so step 1 is to replace that f of x notation with a y. So y equals x minus 1/2. Now for step 2, we have to switch the x and y. And then re-isolate y. So in Algebra 1, if we're trying to isolate a variable, I always leave that variable planted and move anything that is hanging out with that variable to the other side of the equal sign. And so here's a minus 1/2. I have to add 1/2, do the inverse operation to get rid of the minus 1/2 here. And so now the new left side of my equation is x plus 1/2. While the right side is just a y. It's an ugly y. Okay, and so don't box this as your final answer. You still need to use your inverse notation. That's incredibly important as part of the standard. And so our last step is to put f inverse of x equals this equation. And that's the answer you box, and that's how it's going to look on a multiple choice test. Okay, next, f of x equals x over 3 plus 5. Okay, and so step 1 is to get rid of that f of x notation and put a y, and then switch x and y. Now we have two things hanging out with the y. We have a 3 and a 5 that we need to get rid of. The order that you go in matters. You have to take care of the number that is not attached to your variable. And so this 3 I consider attached, the 5 is not. And so we take care of the 5 first by subtracting 5. Okay? And then we can take care of the number that's attached to the variable. So if it were being multiplied or divided. And so this is being divided by 3. To undo division, we have to multiply by 3. And so we have to multiply the entire left side by 3. And so if you want, you can distribute that and get 3x minus 15, or you can actually leave the parentheses. That's okay as well. Both answers would be correct as long as you use your inverse notation. So f inverse equals 3x minus 15 for our final answer. And then just remember, it could also be written just like this. Okay, for example 3, switch x and y. You can distribute this 3, but that would still leave the 3 on this side of the equal sign. Here we can go ahead and just divide by it since it's outside the parentheses. Okay, and then lastly we add 7. The reason why we had to divide first is because it was outside the parentheses. You want to get rid of the outsiders first. Okay, and so now our final answer would have a y on the left side and then an x over 3 plus 7. Make sure that plus 7 is outside the fraction because it joined after. And so other ways you could see this is a 1/3 x plus 7. Dividing by 3 is the exact same thing as multiplying by 1/3, as long as that 3 stays in the bottom. Oh, remember, we don't box it with the y. We have to use our inverse notation. Okay, and so if you're ever on a multiple choice test and you just want to test a point to see if your answer is the right inverse, you can pick a sample input. And so here, if I take the original function and plug in 9, I would get 6 as the output. And so I would then want to plug that 6 into my inverse function and see if I get the original output. Or the original input. So if I plug in 9 to the original, I get an output of 6. And so for my inverse function, if I were to plug in 6, I better get a 9 as the output. Okay. Last example. We have to add 7 first, and then divide everything by 5. And so for our final answer, there's different ways to write this once again. You could write it as x plus 7 all over 5, because that division by 5 was our last step. Or we could write it as multiplication by 1/5, as long as we use parentheses around that x plus 7, because the whole thing is over 5. Or we could even distribute the 1/5. And all of these are equivalent answers. So any one of them could show up on a multiple choice test. And so make sure that just because you don't see your answer, there's not an equivalent form of your answer.